Welcome back to our class. Today, I want to look at new topic. We've been doing algebraic structures, and we're now done with the groups, rings, and fields. I want us to look at elliptic curve cryptosystems. These are very important topic because we'll then apply it in zero knowledge proofs and so on. And even the elliptic curve cryptosystems also apply to there. So elliptic curves, as I've said, they're very interesting, and we just be doing what we want to do on elliptic curves. We want to do operations just as we do for normal operations. We will see how to add points on elliptic curves and so on. Now, it's a very important topic in cryptography and number theory. Now, the other thing that we'll apply elliptic curves to is the public key cryptography, in which we'll be seeing how to generate and validate keys. Seeing how to do that, generating keys, public keys, and then validating the same. Of course, that is towards the end after we've seen how to do operations on elliptic curves. Now, I've noted that elliptic curves are they offer greater security as opposed to other cryptosystems like RSA. We are not saying that they are very secure, quantum secure, but they are more secure than the RSA. You remember that RSA, its security depended on big numbers, factorization of the difficulty in factorizing a composite number, a big composite number into its prime numbers. So for instance, we had two prime numbers, P and Q, large prime numbers, and then you multiply them to get our N. So the security of RSA depended on the difficulty of now knowing what the factors of N are. But the security of elliptic curves does not depend on factorizing of numbers, but it will depend on the difficulty of the discrete log problem. The difficulty of the discrete log problem. That is what it will depend on, the security of the elliptic curve cryptosystems. I've noted here that the keys of the elliptic curve cryptosystems, the keys are shorter and are faster to compute. Unlike the RSA, where the keys would be very long, because we'll be talking about you take two prime numbers which are very big, and then you multiply them, and then again after that you come up with a public key, and it's supposed to be a bigger prime number. Also. It's supposed to be a bigger prime number, and after that you get you then get the inverse of that big prime number. So it has a lot of processes to do that. But for the elliptic curve cryptosystems, we are saying that it will be faster to compute those keys. And they'll be shorter keys. You don't require very large numbers. I've noted where we can apply the elliptic curve cryptosystems. Noted where we can apply that. And also you can apply it in digital signatures. And of course, we'll be seeing that, how to do that. Come up with the digital signatures and apply the elliptic curves. Of course, that will be done on elliptic curve. That will be done when we're looking at elliptic curve digital signature algorithm. We'll be looking at that. Then we will also see how to apply the elliptic curves in zero knowledge proofs, and specifically look at snark building, how it's applied there. So those are the areas that we'll be looking at in this topic. So of course, we begin by knowing what an elliptic curve is. And I've begun by just looking at cubic curves because it's a cubic curve, but it's slightly different. So we'll see what makes it different from other cubic curves. What makes it different from other cubic curves? But it's just a cubic curve. When we talk about cubic curve, what we mean is that if you're given a function x, and x, the degree is 3 plus any other thing, you can say even plus 4x squared, then plus something else, and then and so on. So this is a cubic equation. The highest power is 3. So if the highest power is 3, we call it a cubic curve. But now we'll be seeing how then are they different from the other cubic curves, because not every cubic curve is an elliptic curve. So then when we get to know that difference, it will really assist us. So I've defined an elliptic curve, and I've said that an elliptic curve E shall be using E of a field K. The field we know what it is. We're just talking about numbers. It could be real numbers or complex numbers. This is a field. So I've said an elliptic curve is a cubic equation in 2 variables. So the 2 variables are x and y. So you can see my cubic equation here in 2 variables. It has both x and y. That's what I mean by in 2 variables. Where B1, B2, A1, A2, A3 are elements of the field. Those are just numbers. B1, B2, A1, A2, and A3 are numbers. So these are cubic equations. Generally, these are cubic equations. It's from this cubic equation that we then obtain the elliptic curve. And of course, we've already said we need to know what makes it different from the other cubic equations. Now, this expression that I've just given here is what we call the Weierstrass. The Weierstrass form of an elliptic curve. Now, the Weierstrass form, we have the short one, and we have this. This is a general one. This is a general one. From this general one, we obtain the short one. And the short one is the one we'll be looking at most of our time. Now, in this discussion, I know that elliptic curves can be defined even on real numbers. But since our interest is in cryptography, we will restrict our discussion on elliptic curves on Z of P, where P is a prime number. But of course, I've already said that we can do elliptic curves on real numbers. We can do it on complex numbers, but this does not assist the cryptographers. People of cryptography, and of course, those concerned with security are concerned with elliptic curves over a field of integers mod P, over a field of integers mod P. So that is what we will be interested in. Of course, we'll begin by the general one, where we'll just be looking at integers. And then once we learn the basics, and then we go to mod P. Now, so what I've given here is the general form of the elliptic curve. Now, from this general form, if you complete squares in y and complete squares on the right side in x, because the right side has x, you complete this, if you complete this, and then complete this other side, you come up with a short Weierstrass elliptic curve. And that is what I said we'll be looking at mostly, and this is the form. So I said the above expression can be simplified by completing the square in y and complete the square in x, the cube, complete the cube in x on the right hand side. Now, I don't want to go into a process of completing the square because it's a long process. And of course, completing the cube also is a long process. So, of course, completing the square is not very long, it's easy. Complete the square is very easy. So you're just looking for a term that will make this a perfect square. A term that you can add to this to make it a perfect square. And then you go to the right side and again complete the cube. And you look at what can make it be perfect. But now when you do all that and collect like terms, and then you'll find you then come up with this as the equation of the elliptic curve. That will be. So whenever we talk of the elliptic curve, this is what we'll be referring to, the equation of this form, where A and B are any numbers. A and B are any numbers, and I'm using the word numbers because I said we can define elliptic curve on real numbers, we can define on integers, we can define on complex numbers, and so on. But as we proceed, then we'll be looking at ZB, integers mod B, and in this case, A and B would be elements of this set, which are 0, 1, all the way up to B minus 1. B minus 1. So as we proceed, A and B will be members of this set. But before then, A and B, we just taking them to be any numbers. So it depends on whether you're dealing with it on integers or real numbers or complex numbers. Now, so the elliptic curve of this form is what we call the reduced Weierstrass form or the short Weierstrass form. So when you meet those terminologies, whether reduced or short Weierstrass form, this is what they are referring to. Otherwise, then the elliptic curve equation is the one we began with. The general one is the one we began with, but then this is what we normally work with, the reduced one. The reduced one. Now, so the elliptic curve then forms a group. We'll form a group, elements of this elliptic curve, and we shall see how they form a group. And when they form a group, the identity element will be the point at infinity. The point at infinity. I've used O. This is just O. I've used O to mean point of infinity. So when you are giving the points of the elliptic curve, we shall be seeing how to give those, how to determine those points. And the point at infinity is one of the points. This one is not on the elliptic curve. It's not a point on the elliptic curve, but it then becomes one of the points, but it's not, we cannot obtain it from the elliptic curve. We shall see how it comes about, So in fact, I've noted here, say that it is not a point on the graph. This is not. But when you are listing the points of the elliptic curve, it's one of the points. And of course, and then it comes in to be the identity element. Because the points of the elliptic curve will be forming a group. And as they form the group, what is the identity element? It will be the point at infinity. That will be the identity element. Now, examples of elliptic curves, just the shapes. I'm just showing you the shapes or examples. Like when I drew the curve, this elliptic curve, this is what it gave me. This is what it gave me. Then I decided to draw this. This one is an elliptic curve, and then it gave me this. Of course, before long, I'll be showing you cubic equations that are not elliptic curves. I'll be showing you when do you tell that this is not an elliptic curve and this is an elliptic curve. So it's good also to know so that you can know that this is an equation of an elliptic curve and this is not. So in a short while, we'll be seeing that. But what you notice about this is that this curve is symmetric along the x-axis. The x-axis cuts this curve into two equal parts. That's what I mean. It's symmetric about the x-axis. Even this one. All elliptic curves will be symmetric about the x-axis. The x-axis will cut them into two equal parts. Now, this is not the end of this. This thing continues. This thing continues. It's only that my curve reached here, so that it continues like that. Even this one is continuous like that. But the point there is that they are symmetric about the x-axis. That's the point I wanted to show there. I even drew another one here. This is another example of elliptic curve. You can see this is symmetric about x-axis. This one is another one. And again, you can see it's symmetric about x-axis. The x-axis. Now, so I've noted that as seen from this example, 161 above, the elliptic curve is symmetric about x-axis. And so what it means, therefore, let's see these points. Let's see. What that means that this point will be its own inverse. This point will be its own inverse. But you can see this point. Let me say this is point A, 0A. If that is the case, then this point will be point 0, negative A. Negative A. So the distance from here up to here, the same distance from here up to here. That's what I'm saying. So if this point is A, then this will be negative A. If this point is negative B, then you expect that its inverse will be here. Okay.
Dr. Sako, I think we're losing your audio.
Yes.
I think you're clear now, but we had lost you a bit.
It's okay. And there's somebody who was interrupting me. Now, so above, I was just showing you examples of elliptic curves. And of course, there's something here. There's something here I wanted us to look at. There's something here. Just, I look at it later. But look at this curve. Look at this curve. You see, when you simplify it, it will give you an equation of the elliptic curve. But what I just want to show you is that these points are the points where it's intersecting where it's cutting the x-axis. These are the points I'm referring to. These are the points I'm referring to, where it's cutting the x-axis. So these are the points A, B, and then C. Of course, I'll be looking into that. You'll be seeing, so that if you're given an equation, you can easily draw. Now, if you were to factorize this, you'll find that this point is, if you have to factorize this, you'll find that this point will be there, this point will be here. Of course, this is 0, and this point will also be there. So, of course, when you factorize this, what you get? You get x into x squared minus 1. X into x squared minus 1. But, of course, this can also be factorized. So, this x into x minus 1, x plus 1. So, then this point is the 1. This point is 1. And then the point negative 1 is here. And then, of course, this one is the same as x minus 0. And the 0 is here. 0 is there. Now, when you factorize this one again, you'll find that it has only this factor, x, cutting x, but how many times? So this is a repeated, because it's a cubic equation. This is a cubic equation. So you expect that x has three values. X has 3 values. This is a cubic equation, and you can see x had 3 values. One of the values is 1. Those are the solutions for x, the values of x. One is 1, the other one is 0, and the other one is negative 1. And you can see them when you factorize. This one has 3 values of x also, because of a cubic equation, but they're repeated. They're repeated. So because that's where it intersects the x-axis. They are repeated. So you can try and factorize that. You can try and factorize that equation, that cubic equation. So that's what I wanted to show you, that when you factorize, you can always tell where it's cutting the x-axis. Like this one, you can see it's cutting the x-axis at point C. So this is our point C. Then there's point B, and then we have point A, for instance. That's what we have. Now, implicit differentiation, when you differentiate this thing, we know how to differentiate. When you differentiate this thing, what do you get? You get 2y dy. When you differentiate this, dy dx, when you differentiate 2y, y square. When you differentiate y square, you know how we normally differentiate? Is you drop this and you get it 2y. And because you're doing y, you add there dy dx. When you come on the right side and differentiate this, you get 3x squared. And this one you get a. And these are constant. When you differentiate, you get 0. So what is dy dx? To get dy dx, you divide both sides by 2y. So dy dx, the derivative of this will then be 3x squared plus a out of 2y. And that is what I have here. I've said that using implicit differentiation, we get this. And so what then it means that when y is 0, what happens when y is 0? So when y is 0, when you put 0 here, because it's 2y, when you put 0 here, dy dx then becomes it becomes infinity. Becomes infinity because this is infinity. So I've said, so this is infinity when y is 0. When y is 0, it becomes infinity. That is supposing that the power is, if the numerator is not 0, if the numerator is not, the numerator is any number, if the numerator is any number, and then if 2y becomes 0, then the result of the differentiation will be infinity. And this will assist us going forward. We'll know how this is then important to us. But I've just shown you how to differentiate this, and then we have arrived at this. And of course, again, it will assist us in getting gradient. We need to know how to get gradient. Because if you have 2 points and we are connecting those 2 points, we need to know the gradient between these 2 points. And that's how you get gradient, because this is a cubic equation, then, and it has 2 variables, x and y. You then do implicit differentiation. Now, before we go further, let's know what singular and non-singular curves are. This will assist us to know which ones are elliptic curves and which ones are not. Which curves are elliptic and which ones are not. Because I've said they are all cubic equations, but how come others are called elliptic and others are not? So I've said a cubic equation is said to be singular if this polynomial has a repeated root, where roots are, for instance, we say, for instance, supposing x is 1 and x is 1. So x has same value twice. So if x has same value twice, then we say it has repeated root. And if it has repeated root, then we say that is a singular polynomial. It is singular. But if the roots are all different, if they're distinct, then we shall call it non-singular. We shall say that polynomial is non-singular. And I've said here something very important. Note that only cubic curves with the distinct roots, or the ones we call non-singular, are elliptic curves. That's a very important point. Very important point. Only non-singular curves are elliptic. The rest are not. So it means if they are repeated, if they do not have repeated roots, then those curves will form elliptic curves. But those which have repeated roots will not form elliptic curves. Will not form elliptic curves. Will just be a cubic equation, just be a cubic polynomial, but it's not elliptic. So that is how we tell that this one is elliptic and this one is not. Something else I've noted, I've noted that a curve is singular if this part, the discriminant, if the discriminant is 0. If the discriminant of that is 0, then we say that that curve is singular. So what are elliptic curves? Elliptic curves are therefore curves whose discriminant is not 0. If the discriminant is not 0, then they form elliptic curves. So this is the easier way, again, to tell. If you cannot find the roots, you see, for instance, at this point, you have to find the roots. To find the roots for you to tell this is elliptic and this is not. Now, sometimes that would be a long process. So the easier way, therefore, is by use of this equation. Just substitute the value of A and the value of B. And if the result is not equal to 0, then that cubic equation is an elliptic curve. But if the result is 0, then it's not an elliptic curve. So that is the easiest way to tell if a cubic equation is elliptic or if it's not. Of course, we've said that all cubic equations, but of these, some are elliptic curves, and those are our interest. That's what we're interested in. We're not interested with every cubic equation. We're only interested in those that are elliptic. The non-singular ones. The non-singular ones. Those whose discriminant is not equal to 0. They should not have repeated roots. They should not have repeated roots. The root should be distinct. The root should be distinct. Now, so we talked about singular polynomials, and we've said singular polynomials are those that have repeated roots. And so these repeated roots have names. And that's what I've noted here. I've said the common types of singular points. Those repeated points, the common types. One is the nodes, and the nodes, which I'll be giving an example. This is where the curve intersects itself. The curve intersects itself. For instance, something like that. The curve intersects itself. So this point, therefore, is the node. You can see that at this point, x, the value of x is repeated. The value of x is repeated. So for instance, x could be 1, and x is also 1 at the same point. So this is what we call the node. And then we also have the cusp. The cusp is where the curve changes direction. The curve changes direction, and I'll show you that. For instance, the curve was going the other side. Let me say, for instance, how is it? Cusp. But let me see whether I have an example here. This way, just changing direction. It was going the one side, and then it changes the other side. So the nodes and the cusps, these are the types of repeated roots. Now, so this is just now repetition. This is just repetition. I've said, not that a singular cubic, singular, we know what a singular means, that it has repeated roots. Not that it's this singular, the ones which have repeated roots might have an equation similar to the one of the Wester's form. But it will not be, although it will have an equation. It will not be an elliptic curve. And because of the discriminant, it will not be an elliptic curve. So we've said that cubic equation, for it to be elliptic, it must be non-singular. It must be non-singular. These are the types of, yes, this is the cusp I was talking about. This is the cusp and the node. This is the node where the curve is intersecting itself, and this is the cusp. And see, supposing it was going this side, and then it changes direction. This is another cusp at point 0. So point 0 is appearing twice. And this could be point 1 or what. You can try to factorize this and see. There's a point that is repeated here. And the point that is repeated here, can see it could be 0. 0 is repeated here. But then we have another point here. At this point is, so how do we arrive at this? Supposing this is This is 1. How do you factorize this? Okay. Suppose it's 1. So if it's 1, then what you have is x minus 1 multiplied by x minus 1. Will this be 2? Let me assume that is 2. So x plus 2. So you know what I've done? What I've done here, x was 1 here. And another x was 1. So I just bring this one beside. So I say x minus 1, x minus 1. And then this one, x was minus 2. So when I bring it here, I get x plus 2. So this one I'm trying to multiply. I want to see whether I get this. That's what I'm trying. I want to see. So this and that will be x squared. I'm just imagining that, supposing this. I don't know what it is. I don't know what values I was using when I was drawing this. So this will be x squared, and that will be negative x. I'm just multiplying. And this will be 2x. And then I'll have minus 2. Minus 2, yes. So this is what I want to multiply by x minus 1. So what is on my left-hand side here is x squared, then plus x, then minus 2, then multiply by x minus 1. So when you do this, let me multiply by x. I multiply everything inside there by x. And when you do this, you get x cubed, then plus x squared, then minus 2x. X cubed, x squared minus 2x. Now let me multiply by negative 1. Everything there, the negative x squared, negative x, and then plus 2. So when I correct like terms, I have x cubed, then x squared, and negative x squared gives me 0. Then I have these 2 give me negative 3x, then plus 2. Oh, those are the values I used. So this is the point, x is negative 2. And this is the point, x is 1. And it's repeated. So it gives us this equation. But this equation we are saying is not an elliptic curve because of repeated root. It's not an elliptic curve. It forms a node. A node x is 1. So it's repeated. So this is not an elliptic curve. It's not an elliptic curve. So supposing I was just given the equation and I did not know how it will behave if I drew it. Of course, when I draw it, this is what it gives me. But supposing I did not know how it will behave when I draw it, and supposing I don't want to factorize, then I come back and use the discriminant. The discriminant should not be equal to 0. This is 16, negative 16, multiplied by 4a cubed plus 27a squared. So just put your a there and put your b there, and there's a negative 16. The answer that you get, if it's not equal to 0, then what you have is an elliptic curve. But if it's equal to 0, then you don't have an elliptic curve. And I'll be showing you examples. Now look at this. This has repeated roots. In fact, there are 3 of them. X is 0, x is 0, and x is 0. So when you bring this other side, you have x minus 0, multiplied by x minus 0, multiplied by x minus 0, which is just x times x times x, which is x cubed. So it has a repeated root, and again, it fails to be an elliptic curve. It's not. So these are cusp. These are the cusp we are talking about. It's not a must that it should be at 0. It can even be at 1. It can even be at 1. It can at 1, then the curve changes direction. For instance, supposing this is our point 1, so you can have the curve just coming like that, and then again goes like that. So this is point 1. So what we're talking about, x is 1, x is 1, and x is 1. So that means x minus 1 multiplied by x minus 1 multiplied by x minus 1. This gives you a cubic equation, but it's not an elliptic curve. It's not an elliptic. And the point I'm emphasizing is that once we have a repeated root, that cubic equation is not an elliptic curve. Okay, so in this example, I was just giving the examples of nodes and cusps. And I'm saying that in figure 4A and 4C, you realize that the curve crosses itself, and therefore this type of singularity, as we've said, is a node. But in figure 4B, it's a cusp. So the curve changes direction. So that means all the x values are here. All the x values, x is repeated 3 times. That's what it means. I think that point is clear. That point is clear. I'm just using the same thing. But at this point, I'm emphasizing that if you're given points, you can as well know where the curve is crossing, where the curve is crossing the x-axis. Okay. Now look at this. So supposing this is point A, and this is point negative B, and then x is A, and x is negative B. No, x is A twice. X is A twice, and x is negative B once. So when you cross the equal sign, you have x plus B multiplied by x minus A, then x minus A. And of course, this is what simplifies to this. But this one, this is negative A. So x is negative A. So when you cross it, it becomes x plus A. X plus A. But how many times? 3 times. X plus A twice, x plus A 3 times. Now, this one I assumed that A is, so for instance, this is just okay, so that if A is negative 2, then what you have is x minus 2 square. This is what I mean. That's what I mean. Minus, and then A. Minus, and then A. So I was just, this example was what I was emphasizing, is that if you're given a factorized form, you can tell where this curve actually is going to cross the x-axis. You can tell where it's going to cross the x-axis, and you can easily draw it. You can easily draw it. Now, so that what is most important to us is now, how do we add points on elliptic curve? And how do we come up with the points? And of course, I'll be showing you how to come up with the points, then how to add. But before coming up with the points, I'm now imagining that you've already been given points. Somebody gives you 2 points on elliptic curve, and you're asked to add those 2 points. That's what I want us to focus on first of all, before we come up with how do we come up with the points? Coming up with points is very easy. Just put the values of x, and you get the points. Now, so because of this, I've said that one property of elliptic curves that make them useful is that if you're given 2 points that lie on the curve, we can construct them. We can add those 2 points, and when you add those 2 points, you'll get another point on the elliptic curve. So if you're given a point P and Q, if you add these 2, what you get is another point on the elliptic curve. And this is the property we've been talking about, the property of closure. The property of closure. That's what we've been talking about in groups. And you have any 2 points. And of course, elliptic curves, we're looking at them in terms of as additive groups, as an additive group. And I've said that this additive group, the identity will be the point at infinity. So when we take 2 points and add them, what we get will be another point on the elliptic curve. And this is very important. It's a very important property. It makes it a group. And in security, cryptography, we're interested with those groups, of course, in terms of security. Now, so if you're given these 2 points and you're asked to draw a line through them, you're asked to draw a line that passes through these points. Let me say a point Q, and point P. And okay, let me draw the elliptic curve first of all. Supposing this is my elliptic curve. I have point P and I have another point Q. I have another point Q. And I want, you see, this elliptic curve continues. That's what I say. Continues. Now, if you draw a line through this point, a straight line through these points, you discover that this straight line, if you elongate it, it will cut the elliptic curve at another point. Only one other point. You cannot cut it 2 times. You cannot cut it. Okay, it has cut it at this point, it has cut it at this point. You are connecting in these 2 points. So when you extend it, it will cut the elliptic curve at another point, 3rd point. This 3rd point, it is perpendicular. Its inverse is the sum of these 2 points. So supposing I wanted to add P and Q, I would draw a straight line through them. This straight line will cut the elliptic curve at another point. Then I draw a perpendicular line. This point, let me say R, becomes the sum of these 2. Becomes the sum of these 2. And that's a very important thing. And you'll be seeing how to do that geometrically and how to do that by just adding. So I've said, if a line is drawn through any 2 points on the elliptic curve, this line will intersect the curve at another point. This point of intersection is then reflected through the x-axis. To give the sum of the 2 points. That's what I've just said. That I've been given these 2 points, and the question is add them, get their sum. So I just draw a perpendicular line, a straight line through them, and elongate it to cut the curve at another 3rd point. Then I drop a perpendicular line. Of course, I'm assuming that my x-axis is somewhere there like that. Somewhere. X-axis is cutting this curve into two equal parts. So I then drop a perpendicular line through the x-axis. When I touch this curve at another point, this other point is the sum of the 2 points given. It's the sum of the 2 points given. So you can see how easy it is to add points on the elliptic curve. If you have it drawn, it becomes very easy. That you then just draw a line passing through the 2 points, and this line would then cut the elliptic curve at another point, and this other point becomes the sum. So that then gives me the definition. I'd already stated about the inverse of a point. I've already stated. If you're given point A, and if point A is AB, then the inverse of A, and addition, this will be A minus B. A minus B becomes the inverse. And when you add these 2 points, because they're inverse of each other, you must get the identity element. You must get the identity element. The identity element we said is the point at infinity. You remember that? And this point we said is not on the curve. Is not on the curve. Now, so what have I said here? What I've said here is this. What I've said in my definition is that supposing this is my x-axis, and supposing that this is my elliptic curve. Okay, I'm not drawing properly. It's supposed to cut into equal parts. So supposing this is my x-axis, and supposing that this is my point P, and this is my point Q, and I want to add these 2 points P and Q. I've said I'll then draw a line through them. And this line I extended to cut the curve at another point R. Now, after it cuts it at R, I'll draw a perpendicular to cut the x-axis and then come and intersect this curve at another point. This point is the inverse of R. Is the inverse of R. So what I mean by that is that if R is xy, then this point is x negative y. X negative y. The minus is only on the y coordinate. The minus is only on the y coordinate. That's what I've written here. That's what I've written here. That's what I've said. If 2 points P and Q are on the graph, but they're not on the same vertical line, then their sum will be negative R. Their sum will be negative R. That is their sum, negative R. And you know what R is? R is this point. This is not the sum of these 2 points. This is not the sum. After you've gotten R, you reflect it through the x-axis to get R inverse. R inverse is the sum of these 2 points. That is what this definition is saying. So I wanted to understand my definition there. Okay. Now, so a very good point is here. A very good point I've said, if they're not on the same vertical line, if they are not on the same vertical line, let me again draw my curve. If they're on the same vertical line, suppose this is a vertical line. The curve is here. The point is here. So the other point is, of course, here. They're on the same vertical line. So these ones, we cannot add them the same way using this method. You cannot add this point and this point using this method. These 2 points are on the same vertical line, it means they are inverses of each other. They are inverses of each other. Their sum, of course, is identity. Their sum is identity. So you don't add it the same way we did add. If they're on the same line, what I mean is this. If this is x and this is y, if they're on the same vertical line, then we expect this to be x and this to be negative y. So they're inverses of each other. And if that is the case, there are some, of course, you don't need to disturb ourselves. It's just identity element. It's identity element. If they are on the same vertical line. But if they're not on the same vertical line, then you then join them with a straight line, and that straight line will cut the curve at another point. Cut the curve at another point. Let me see. Supposing I have this what I have. Suppose this is what I have. And I have this point P, and I have this point Q, and I want to add them. I would join them with a straight line. It has cut, this is my R, and of course my x-axis is somewhere here, cutting the curve into two equal parts, my x-axis. So I reflect this through the x-axis, and I get R inverse. This R inverse is the sum of these 2 points. So that's how you do it. That's how you add these points by construction. But of course, we'll come up with an easier way of doing it again using gradient. Using gradient, we shall look at that again. So what does this definition say? This definition says if P is not a point at infinity, it's not a point at infinity, you can draw a tangent line to graph at P. Oh, so this, I want to add a point to itself. I want to add P to itself. That's what I want to do. Good. So I have this x-axis, and I have this point P. I have this point P here. I want to add P to P. P plus P. What do I get? What I've said here, I'll draw a tangent line to this curve at P. A tangent line is a line that touches the curve at only one point. Touches the curve at only one point. So it touches the curve at this point only. Then this tangent line, I elongate it. I elongate it until it meets my elliptic curve. So the elliptic curve was that way. So it has met the elliptic curve at this point. So once it meets the elliptic curve at this point is R. That point is R. I get its reflection through the x-axis. It's a reflection through the x-axis. My R inverse is the sum of P plus P. The sum of P plus P is my R inverse. So that's what I wanted, this definition 40. That's what it was talking about. So I want to add a point to itself. This is what we call point doubling. And it's a very important tactic in this elliptic curves cryptography. Point doubling. So you have, this is the equivalent of what we are looking at, successive multiplication, we'll call it successive or fast powering algorithm. So, for instance, if you have P, you want to get 2P, you want to get 4P, you want to get 8P, you want to get 10P, you want to double these points. 16P and so on, 16P. Of course, if I wanted to get 10P, I would first of all I can get this 8P, and so this would be 8P plus 2P. But this is point doubling. You see, I double this to get this, Then I double this to get this. Then I double this to get that. Then at this point, I think of how do I get this? Then I remember I need to add those two. But how do we double a point? Geometrically, I've said it. Geometrically, I've said it that if this is my curve, elliptic curve. I've not drawn it properly, but you know how it's supposed to be. Elliptic curve. And I have point P. Point P. If this is my point P, I draw up a tangent line, a line that touches this curve at only one point. So if this P is there, then I can see my tangent line will be a line like that. I elongate it. You can see it has touched my elliptic curve at this point. I reflect this point through the x-axis. This is my x-axis. I reflect it. My 2P is here. My 2P is there. So that's how you double a point. And of course, I'll show you a method that you can do without constructing. But what I'm doing this by constructing, just so that you can just understand how do we add a point on the curve, how do we add a point to itself, how do we add 2 points which are separate, which are distinct, and so on. Somebody might be having this question that why do you have to pick a point that is reflected and not the one that intersects? That is supposing you see, this is what I'm talking about. This is what I'm talking about. When you had P and you had Q, and let me say P and Q. When you had that and you joined, we picked the point. This is where it intersects, but we didn't pick the point of intersection. We reflected. So somebody will be wondering, why are we not picking just where they're intersecting, and we are going to the reflected one? And the question has to do with the group. The group. So I've said the reason is since the points on the elliptic curve form an abelian group, each element of the group should have an inverse. So reflecting it ensures that the point we obtain has an inverse. It just ensures that this point that we're getting has an inverse. Of course, the point we picked is the inverse of the point that was got on intersecting. When they intersected, the point that we got, we went for the inverse. So this is just to ensure that our points are, we have every point has an inverse, just to ensure that every point has an inverse. That's why we do it. This point is just to remind you that if P is this, then its inverse, we just change the sign of the y coordinate. We change the sign of the y coordinate. So if the y coordinate was -2, then it becomes +2. And if it was +5, then it becomes -5. So just that's what we, and that becomes the inverse of that point. And again, this point has also reminding you that the point at infinity is the identity element of the group. So that if I add the point of infinity to P, what I get is P. And if I add P to its inverse, I get the identity, the O. This is just O, it's not anything else. I just took O. It's just capital O, this one. If you want some books just use infinity. Some books use infinity. So you can just use infinity. It means the same thing actually. Now, let's now come to workings, examples. Examples. Consider this elliptic curve. I want to add P to Q. This is what I want to do. So I would first of all identify my P, 2, 3. 2, 3 appears like somewhere here. This is my P. And then Q is 0, -3. 0, -3 appears like somewhere here. So this is my Q. I want to add this. So what I do then, I would join them with a straight line. This straight line is supposed to, I've not done it properly, but I know it will intersect this curve at some point. Intersect this curve at some point. Supposing it intersects here. Supposing this is a point, it has intersected the curve. I reflect this point through the x-axis, just drawing the perpendicular line. So this is my R. I come up with a negative R. So therefore, this point is the sum of the 2 points given to me. It's the sum of the 2 points given to me. So that's what I then do. That's what I've been doing. And I've explained it in my working here. Explained it in my working. I've said first, you draw a line through P and Q and extend this line to intersect the curve. You can see that's what I've done. I've drawn a point, a line through these 2 points and extended to intersect the curve. This way it intersects the curve. At R, so I call this point R. And then the second procedure I've said, now draw a vertical line through R. It hits the curve in another point. This reflected point is the sum of the 2 points. So you can either call it this way, or some books you will use this symbol. Some books will use that symbol. It means the same thing, sum. It means summation. So this is our negative R, which is P plus Q. This point. So it's the same thing here, the same thing I've done. I've been given 2 points, A and B, and the question is, the curve, I've been given this elliptic curve. Of course, we need to find out whether it's elliptic curve. I had found out, but in the next examples, I'll be showing you how to, using the discriminant that we mentioned above. So the question is, find A plus B, then find this C. Look at this. This is associativity. This is associativity. I'm just adding A plus B, associativity. So we can do all those properties of elliptic curve of groups over here on the elliptic curve. But it's very simple. What I've done, I've just identified the A, 1, 2. 1, 2, that appears like this point. And then 3, 4. 3, 4. 3 is here. Then 4 is here. So this is my Q. No, my B. My B, and this is my A. So then I join these 2 points with a straight line. This is where it touches the x-axis, the curve. This is my R. My x-axis is here. So I reflect this R through the x-axis, drawing a perpendicular line. It touches the curve at this point, negative R. So this is therefore the sum of these 2 points. This is A plus B. This point is A plus B. So you can see from my knee, it appears like it's -3, -3, 2. It appears like it's -3, 2. But this one is what? -3, -2. So this is just the inverse of that. Just the inverse of that. And then the question was now, after I've gotten A plus B, add that A plus B to A. Add it to A. So I've gotten A plus B. So A plus B is this point. This is A plus B. I want to add it to A. What that means again, I draw a line through these 2 points, then extend it to cut my curve at another point. This other point reflected through the x-axis to get the sum. You get the sum there. Yeah, so you've learned a lot of things about elliptic curves today, and those are just the basics, so that we'll be building on those basics. And of course, I've said that then we'll be looking at formulas of how to add elliptic curves, points on elliptic curve, without constructing. But using construction, we've seen how to do that. Using construction, we've seen how to do that. Now, this one, I'm just explaining the same thing. This one, I'm adding point P to itself. I'm adding point P to itself to get it to P. And so, what is point P? 2, 3. 2, 3. It appears like this point. So, this is a point to itself. So, what we said, add P to itself, we have to draw a tangent line through this point. A line that cuts the curve at only one point. And then this tangent line, elongate it so that it touches the curve at another point, so that it intersects the curve. So you can see it has intersected the curve at this point R. Get the inverse of R by just reflecting through the y-axis. So this inverse is the sum of P. So 2P therefore is negative R. This point. So that's what I'm explaining here, how to get the sum of a point, adding a point to itself. So this is what this example is then talking about. Then it also tells me that after adding 2P, after getting 2P, use it to get 4P. So we had gotten 2P to be here. To get 4P, I added 2P plus 2P. So it means I have to draw a tangent line through this point. Draw a tangent line through this point and elongate this tangent line to cut the curve, another point. My 4P becomes the inverse of this point. Comes here. So it's very easy getting 2P, even getting 8P. So if I have this 4P, this is my 4P. If I want to get 8P, I would again draw a tangent line through this point. So it's 4P plus 4P. Then this tangent line, elongate it. You can see it cuts at this, then reflect it through the x-axis. Get 8P. Every time you add any point, the point you get is again on the elliptic curve. It cannot be outside. It's on the elliptic curve. So that's what I was just explaining. I was explaining what I then be doing. Drawing the tangent line, then reflecting the point of intersection to get the other point. So that's what I'm doing. Now here, I've been given A and B, and I want to get it to A and to B. And again, it's the same thing. Identify. So that means I must add A to itself. I come to where A is 1, 2, 1, 2, 1, 2. 1 appears like somewhere here, then 2. So this is A. I draw a tangent line through that. You can see as I draw this tangent line through this point, this tangent line cuts the curve at this point. It cannot cut it at another point, even if you are to elongate it. Do not cut it at another point. You just cut it once. So it cut it at this point. Then reflect to get to A. What about 2B? 3, 4. 3, 4. 3 appears like somewhere here. 3. Then 3, 4 should be here. Draw a tangent line, and this is my tangent line. It comes and then it cuts the curve at this point, intersects the curve at this point. Come and read 2B. This is 2B. The reflection of this through the x-axis. Now, so in fact, I was just showing you how to note how I will be adding. And then this addition, now the formula that we'll be talking about is derived from this. It's derived from all these things we talked about, these reflections and so on. So this is where we then come up with that formula. So that is the formula then is what we'll be looking at next time. That's what we'll be looking at next time. Let me just take you back here. Take you back here because I've seen there's no I've touched on the use of the discriminant. I think it will be coming later. Let me go back to where the discriminant was. Where was the discriminant? We are using the discriminant to tell if the curve is elliptic or not. So supposing my curve is y square is x squared cubed minus 3x plus 2. I want to see whether this forms an elliptic curve. Now, so the discriminant should not be equal to 0. So my A in this case is -3. So I just put -3. And my B is 2. So I just put 2 here. So what is -3 cubed? -3 cubed will be -27. Just use my calculator. So that would be -3 cubed will be -27. I want to take this -27 times 4. This gives me -108. Then what about 27 times b squared? B squared is 4. 4 times 27, that gives me 108. 108. So inside the bracket, I have -108 and then plus 108. This gives me 0. And outside, I have -16. So this thing is 0. This thing gives me 0. Because it is 0 times -16, it is 0. So it means this curve is not a curve of is not an elliptic curve. It's not an elliptic curve. So if it gives you 0, it's not an elliptic curve. But if it gives you something not equal to 0, then it becomes an elliptic curve. For instance, if I change this sign, to be positive 3x, then this becomes positive. So inside, I don't have a 0. So what we see is not 0 times what is times non-zero. So non-zero times non-zero gives me non-zero. So this now becomes an elliptic curve. So that is, I just want to emphasize, how do you tell that this curve is elliptic and this one is not? And I've used the discriminant. I've used the discriminant to show that. So I want to stop there so that when we next time, then we look at how to add points on elliptic curve using a formula. Thank you.